And
Okay.
the Flying V video made a huge success down here. Everybody went crazy about the design, and they wanted to know more about how it flew, and so
Okay.
that's where my idea came from.
Yeah, yeah, no, I totally understand. I mean, it's great. It's so weird what has happened, over the past 2 weeks, after we did that press conference. I mean, it's just gone really crazy, really crazy. Oh, completely out of our control once you
No
bring
kidding.
something into the world.
Yes, yes.
But
So
yeah, just go ahead. You can ask me anything,
all right.
anything you want. I'll try
So
to answer to the best of my ability.
okay. So first of all, thank you so much for being here, for giving out this interview. I'm sure my audience, and even though people are gonna find this video, they're gonna find it really cool and really awesome. So thank you so much for your time. And first things first, please educate us on the correct pronunciation of your name.
It's Roelof Vos.
Vos. Okay. So we are here today with Professor Vos, and he is the project lead and the team lead of the Flying V. Is that correct?
Yeah, absolutely.
All right. And you probably been seeing the video on the internet. It's a V-wing shaped new concept of an airplane. And so first of all, tell us a little bit about yourself and how you came into the project.
Okay, so I'm an assistant professor at Delft University of Technology in the aerospace engineering faculty, and I've been working in the field of technology assessment for about 1 decade. So there we look at all kinds of different technologies that can make aviation more sustainable. So we particularly look at how to reduce fuel burn, and also how to mitigate climate effects that airplanes cause. One subset of technologies are the new airplane configurations. So in the past, we
Okay.
studied also blended wing body airplanes. And about 5 years ago, approximately, maybe a little shorter ago, we started with the Flying V project, where we looked into what this Flying V shape could do for fuel burn. And the project actually was initiated at Airbus by a student at the time by the name of Justus Beenat, and Justus actually is the inventor of the configuration.
Okay.
And what we basically did in Delft is we looked at that configuration and we modified it a bit. So we brought another innovation into it, which was an oval fuselage structure.
Hmm.
So more of a concept on how to integrate a non-circular structure into this wing that you still need to pressurize, right? Because that's of course quite a challenge there. So we basically married the V-shaped planform with this oval fuselage structural concept, and that became basically the foundation of the Flying V as we have basically been investigating over the past years. And then about 2 years ago, no, but yeah, about a year and a half ago, we acquired some decent funding from our sponsor, from KLM. They were
Okay.
celebrating their 100-year anniversary, and basically, as part of that celebration, they donated a substantial amount of money, such that we could build this scaled flight testing article, and that we could also build a mock-up of the cabin and really do some more fundamental research in what it means if we will be flying in such a V-shaped type of airplane.
Nice, nice. And this, as far as I had the contact with KLM professionally, I've been to Schiphol for a couple of times for work, and they do have this trait in business wise of bringing a greener aviation, right? So to say.
Yeah, I mean they have a very strong motivation to make aviation more sustainable. They employ several types of initiatives,
Hmm.
and that's why we saw that the ambition of the Faculty of Aerospace Engineering at TU Delft and the ambition of KLM was quite nicely aligned. And the whole meeting and where we pitched this idea was actually very very short. It was like we agreed on everything. So very fruitful, and in a very short time we got together and we started this project of building a scaled flight test demonstrator and building a mock-up of the cabin to cover those two very distinct bases, let's say.
All right, and this leads to one of my first questions, which is why a subscale or a scale flight test bed, or why many people wonder, well, wouldn't it be easier just to make the full airplane? And so tell us a little bit about that, why you went to a smaller airplane, and the advantages and disadvantages that you found on that approach.
Yeah, no, that's definitely a valid question. So the reason why we went to a scaled model rather than a full scale model lies in the cost. I mean, just generating a prototype full scale would be very expensive to build. And before you actually want to make that step, you want to be very confident that that airplane that you're building and you're putting all your monetary funds in is actually going to work. And I think there was quite a number of question marks that we still had that we could also solve with a scaled model. So, for example, how does the airplane fly? Is it controllable? Is it stable in the air? Can it actually take off from the ground? Do you have sufficient control power? How does it maneuver on the ground at high speeds, for example, tipping over? All of these things we could actually test with a scaled model. So that's why we went with this scaled flight test demonstrator first, to sort of tick off some of these boxes. And one of the things that we also tried to do, and that made it a little bit more ambitious than just the demonstration, is to take good measurements, not only from the accelerations that the airplane was experiencing, but also measuring the flow angles that the airplane was experiencing, to deduce from the scaled flight testing model the so-called state space model of the flight dynamics model, and from that, with the inertia, derive also the aerodynamic model of the airplane.
Okay.
And that's what we're currently actually doing. So we've got the state space model, and we're now looking into if we can actually derive the aerodynamic model. And the reason why we think that is an interesting step is because once we have the aerodynamic model with some scaling laws, we can actually make a simulator model of the full scale airplane and actually present this to pilots and say, hey, you go and fly in this simulator and tell me what do you think? Does this have good flying qualities, or what should we improve? Where can we do better? And there's already from this flight test we have a number of points where we already said, okay, we got to improve here. We got to change that how we deploy the control surface when we do for example. But that gives a little bit of perspective on the scaled flight testing model in the broader sense of developing this aircraft and investigating the characteristics of this aircraft.
Nice, really nice. Yeah, and where if you had to name the most important data that you collected so far, the good and the bad, what would you say? What did you observe from the model that surprised you? Said, well, this was not supposed to happen, and what was really good? And you can say, well, this is right on the dot, just like the theoretical model predicted.
Yeah. Now, so to start with the latter, in terms of what we predicted, is we basically first built a half model of the same scale as the flight testing model and put that in the wind tunnel.
Okay.
And we've actually done quite some wind tunnel tests prior to the flight test to determine particularly how the pitching moment of this airplane is changing with angle of attack. So we get quite some interesting aerodynamic phenomena over this highly swept wing. We get formation of vortices on the upper surface. And so we did quite some predictions on the half model, but we also saw that half model wind tunnel testing itself has its limitations. And so based on the wind tunnel model, we predicted the location of the aerodynamic center of the airplane. So basically the location on the wing where the pitching moment does not change with angle of attack. And I think we expected it to be a little bit further aft than it actually was. So that meant the airplane was less stable as we predicted. We looked at the data now, and we think, based on what we measured, that the airplane was still stable, but marginally.
Okay.
And that meant that the pilot needed to put quite some control inputs to let it fly straight. So what do we learn from that? For the next flight, for the scaled flight testing model, we would basically position the center of gravity a little bit more forward. Probably the wheels, so the axle of the main landing gear probably needs to shift forward also a little bit. We can do the shifting of the CG quite simply by shifting the batteries inside a little bit more forward. The shifting of the landing gear takes a little bit more effort. So that was one thing on the static longitudinal stability. The other thing that we didn't know is how it would behave dynamically.
Okay.
So together with Airbus, we had looked at the flight dynamics prediction of the airplane based on linearized models, and we already expected that the Dutch roll could be an issue. I think what we saw in the flight test that there was a very strong roll yaw coupling.
Okay.
Call that Dutch roll.
Yep.
The airplane was doing this a little bit, and particularly when we put in aileron, then we see that motion is sort of initiated, and then we started thinking about that, and it makes total sense because we have this winglet sitting here right next to the aileron. So whenever we basically deflect the aileron, let's say trailing edge down, for example, we would generate some suction on the upper surface, and that would also provide suction on the winglet that would basically yaw the airplane in the exact opposite direction
that you wanted.
So this very strong coupling between roll and yaw, sort of an adverse coupling, is something that we sort of witnessed firsthand in seeing how that model responded to control input. So one of the next steps that we want to do is see with proper control surface allocation, so maybe not using the outboard control surface for roll control, for example, or by mixing in the rudder there, can we actually improve the response to control surface input? And I think we can. I mean, that's the beauty of if we derive the aerodynamic model properly from this test, then we can use that to test, let's say, some kind of control allocation ideas, and then maybe in the next test we implement that in the control laws for the flight test model and see how that behaves. And that's also another thing, a great thing about scaled flight testing. I mean, you can actually do that and test out these ideas in real life and see how the airplane responds to it.
Nice. Really nice. And this is something, the coupling is something that the HEF model would never give you, right? Because you are not able to measure the lateral directional coupling. So really, really, really nice. And were you flying on this first flight? Were you flying completely, let's say, direct mode? You had no onboard electronics or fly-by-wire trying to help the pilot. That was just pilot.
Yeah. So basically, we use the Pixhawk flight controller, which has a auto-stabilized mode in there that you can just turn on, let's say.
Okay.
Of course, you have to set the gains a priori, and that's something that we want to do in the future, just to see if you just use a sort of standardized auto-stabilized mode, would this damping maybe already be in there? Could be. But for the first flight, we wanted to have it direct because to be honest, we had no idea how to set the gains on those flight in those flight control laws that would be in the Pixhawk. So we first wanted to just see how it would fly manually before we go to some kind of autopilot mode.
Nice. And how do you compare the Flying V? You already talked a little bit about this, but how do you compare the Flying V to other tailless flying wings and BWB designs and blended wing bodies? What do you say is besides the obvious V shape? But what are some of the advantages and disadvantages of the Flying V against the regular BWB, even though it's another unconventional configuration as well?
Yeah, I think if you just start with the disadvantages, to be fair here, I think compared to the BWB, probably the BWB can have a little bit more better volume to wetted area ratio, let's say,
Okay.
than the Flying V. So I think it can have a little bit more volume for the same outside area than the Flying V. The reason that the Flying V, I think, is from an industrialization point more interesting than a BWB is that it can much more easily be stretched or shrunk. So we designed it as a 3-member family, and because you have this constant section in either side of the V leg, let's say ahead and behind the engine, you can cut out part of it and put it back together and make a shorter version of it. And that is something that is not impossible to do in a BWB, but it's a lot harder to sort of make that puzzle. And that is something that when I first saw the Flying V and I saw the original idea that that Justus actually put forward, he basically put these two A320 fuselage barrels in there, and I was like, we could actually make a family out of that. I could sort of mentally picture how that could work. It turned out that my initial idea turned out a little bit more complicated than I had initially thought, but it can be done, and it's not so hard to do. And you can basically recycle, let's say, 95% of the components in all those 3 family members. And that is, I think, a big plus if you talk about industrialization of such a flying wing airplane, because I don't think neither Airbus nor Boeing nor Embraer, for that matter, is going to want to do a one-off long-haul airplane. It's just too expensive. You want to invest your money and then cater for a larger market. So now we're catering for the 200. I think the smallest version now looks at like 290 seats in a standard 2-class configuration, and the largest version looking at a 360 seat airplane in a 2-class configuration. So I think we are basically covering the same market that, let's say, the A350-800 until the Dash 1000 would cover.
Okay.
The Dash 800 was, of course, never built, but that was sort of the rationale. And that is something that I think sets the Flying V apart from other flying wing designs.
Nice. Really good. And how does this new shape, the Flying V, brings, as you mentioned in the beginning, the environmental sustainability that we are looking for in aviation regarding fuel burn, especially, and maybe noise for the community? How do you see that changing?
Yeah, so we really have the ambition here at TU Delft to make a decent contribution to the climate neutral aviation. And I know that the Flying V is only one step in that direction, and it's not going to be, the silver bullet that what we are all looking for. That probably has to come from a whole basket of different types of technologies. But definitely, this could be a contributor, because basically what we're doing here is definitely not magic, right? If you zoom out, we basically see an airplane that it has just a little bit smaller wetted area than an A350, has a little bit more effective span due to these high winglets, and it has a lower structural weight due to the fact that you distribute the weight also where the lift is. And that has the advantage that the overall structural weight is also lighter. So you have this combination of less weight, a higher aerodynamic efficiency, and if you combine these two, they translate over such a long mission range into a 20% reduction in fuel burn.
Wow.
So that is, I would say that is already definitely something, particularly because we're not changing the engines, right? So the engines are still your Trent 1000 turbofan engines. So
they're off the shelf. I mean, you can go and get the engines right now if you wanted, with no new technologies.
Right. So we wanted to really see what would be the impact of the Flying V airframe technology, rather than coupling that to all kinds of fancy materials or new propulsion techniques, or maybe even hybrid electric stuff. So we really wanted to make it sort of as fair as possible, Making the comparison based on the same functionality and also on the same engines.
Nice. Good. And a lot of people have asked me, when can go in a store and buy the Flying V so they can fly at their own clubs, like my little wing here.
Oh,
A
so
lot
yeah,
of
yeah.
a lot of people are really interested in having a model version of the Flying V. So when
So
will
maybe
it come to stores?
we should start a spin-off company, right?
Well, maybe. There's
This might be
the
commercially interesting, right?
yeah, there's the little KLM store at Schiphol with a lot of cool stuff. We could just sell it there.
Yeah, so maybe this idea. I'd never actually thought about that. So I don't know. Could be something to pursue. But for now, I mean, we're sticking really to the research side, and we basically what we're doing with the scale flight testing is investigating the flight dynamics, handling qualities of the airplane, really in service to making this airplane a full scale version that could be a serious competitor to the existing tube and wing aircraft. And there's still so much research to be done there. That's actually what we're focusing on here.
Nice, and this is a very good point that I think it's important to make for our audience, is that this is a research model, right? So you're using this
Absolutely.
for science and for the development of a better aviation and a better usage of the airspace, right? And this
Absolutely.
and this brings me to another question. How do you see this has maybe less to do with the scale model and more to your full scale mock-up, but how do you see the user experience changing? I mean, for people that are going to be flying the Flying V and they're going to be customers of KLM and other
Yeah.
companies, how will
Yeah.
the user experience change? Will they have to are the seats going to be a little different? The boarding and unboarding of the airplane is going to be a little different. So what
Yeah.
are your insights on that?
Well, there's a couple of things that you just mentioned that are going to be different. Boarding and deboarding is going to be different. Instead of having just a twin aisle airplane, we are now having a 4-aisle airplane. While we haven't actually investigated what that means through empirical tests, what that means for the boarding times, for example, we can already imagine that having 4 aisles might make the boarding and deboarding a little bit smoother.
Okay.
From the passenger comfort point of view, we are working very closely with our industrial design engineering faculty. Professor Peter Vink has been a collaborator on this project from the very beginning, and he's looking in different types of innovations with respect to the comfort of the passenger. And one of the things that he's, for example, looking at is rotating the seats in the flight direction. So imagine we have these two oblique legs of the Flying V, and if you put your chairs parallel to that side, you're actually not in the flight direction anymore. That begs the question: what happens if we rotate the seat a little bit and actually put them in the flight direction? And that has already sparked some very interesting results, because as you start to rotate the seats, you start to stagger them a little bit. And that means that no longer are you wrestling with your neighbor for the same arm space on the armrest, but you also staggering that. So those are it's just an example of one of the topics that we're looking into. Also different ways of storing the carry-on luggage, because we have this new kind of structural concept for the fuselage that definitely brings about some challenges in terms of additional structural members within the cabin, but it also gives you new opportunities of thinking about, hey, how can we do that storage of the overhead luggage? Could we maybe utilize the space above those cross beams that we have, or maybe utilize the space that we have next to the last chair, next to the window? So definitely we're looking into that. The bottom line is that the comfort levels that we propose should always exceed what we have now and can never drop below. That was from the very beginning a very important top level requirement, that we don't cram in all the passengers onto a very small floor space and say, well, we have a very efficient airplane, good luck with it. That's just we try to keep the balance between comfort for the passengers, but still have a more fuel-efficient airplane.
Nice, really good. And very briefly, just so we wrap up here, I don't want to I know you have a busy schedule and I don't want to overstay my welcome. And so what are the next steps?
Multiple next steps. I mean, together with collaborators from industry and academia, we developed a roadmap of actions in the various subdisciplines of aeronautical engineering. And so we're collaborating with a lot of colleagues here within the Faculty of Aerospace Engineering, as well as industry and other universities and research institutes to carry that out. And that goes from emergency evacuation tests to flight simulator tests in the simulator, to aerodynamic analysis at high angles of attack, to the structural design integration of, for example, that engine structure. So it basically covers all the disciplines, because a new airframe shaped like the one we proposed basically impacts all of these
every discipline, right?
Disciplines. Mm-hmm. Yeah, so that's a long list of activities to be carried out.
Nice. So we all wish you the best of luck with the design and the project, and we will be happy to see new videos and new posts from at your channel, and with successful flights. And we are happy to hear about the news coming out. I would like to immensely thank you for your time in this little interview, and I'm sure that everybody's gonna love the information that you put out.
You're more than welcome. It was a pleasure.
Okay, all mine. So
right,
I wish you a good afternoon, and all the best with the new endeavors with the Flying V.
All right, thanks, Jose. Appreciate it.
Thank you so much.
All right, bye bye.
Bye bye.